Hello, I'm Carlos Granja, a scientist and nuclear engineer in ADVACAM. I show you in one of our instruments that we have on board a telecommunication satellite from OneWeb, which is a large USA and UK company. There you can see it's a large size satellite, and our detector is there already flying since 2023 to measure radiation in orbit in high resolution. The instrument looks like this. It's fully designed and manufactured by ADVACAM, and there in the middle you can see myself in the offices of OneWeb, where they have the control center where they handle data from the 600 satellites, including this experimental satellite JoeySat with embedded electronics. And there you can see data that we measure. So these are these microscopic scale tracks of energetic protons, charged particles, X-rays, which the detector registers and is able to analyze in high resolution. Very often space missions like this one require a degree of customization of the device. So it's not just the chip, but the electronics, the interface. There are many advantages which together make the product and the technology very convenient. Starting from the what I call engineering parameters, details that the instrument is very small, as you may have seen, so you can hold it in your hand. It's low power, it's low mass. It requires no collimators for directional response of energetic charged particles. That's a big difference, and it's novelty in the architecture, in the technology. And then the physics parameters, that with the same instrument we can separate different components of radiation, as is indicated. The data then is analyzed post-processing. We do also that here in ADVACAM in part of this contract, so this scientific post-processing work. And there you see what we call radiation maps along the orbit. It's on one side is data from the solar storm that occurred last year in May, and the other map is normal conditions. And the color scale is logarithmic, so there are significant differences. The radiation field changes thousands, even million times in terms of intensity, changes in composition and direction. So there are many parameters and data that we are able to measure, characterize with our small miniaturized instrument. Results in the information provided includes the composition we call, so we separate components in terms of X-rays, electrons, protons, as you can see here. This high-resolution data that we are providing fulfills several needs in space engineering, in the space industry. One is called radiation effects, so it's to study, analyze damages, influence, effects that ionizing radiation has on components of the satellites. The solar panels, the chips, the components, the power supplies, the antennas, they are sensitive to radiation. It's necessary to understand, to protect them. This is one big field, the main purpose of this. And the second, also just as important, in fact, is space weather. So when the data is of high resolution and high physics value, it can be used for science and to predict and to analyze radiation-related events in orbit in outer space in frame of space weather studies. And then there are further applications. One more is science, direct science. So there are events in the sun or in the solar system, galactic cosmic rays, which we also register with our device, and the data can be used also for science groups. And this information is important for the industry, for the manufacturers of the satellite, and the teams providing instruments, and for the operation of the satellite. So the work is ongoing, and there are interesting potential further applications in further satellites, not just in this constellation.